Okay. Can everybody hear me? Okay, so I think we can start. Thank you for coming. It's an honor and a pleasure to be here today to talk about this project we have done at Swisscom. The presentation is called Automatic Site-to-Site Failover, and what is special about this project is that that's actually what it brings us here today, is that we have only used open source software to implement this site-to-site failover. Well, I work as a Unix sysadmin in a small group at Swisscom. We use a lot of open source. We don't choose open source on purpose. We try to choose either open source or commercial software, whatever it's best for our job. But in this case, choosing open source, it just came as a natural process because whatever were our needs, the open source did the job and did it very well. So I hope you like it. In the next 30 minutes, I will present the project, some of the choices that we had to do while implementing it. I will talk about the catches, some of the constraints we found while doing this. I will give you some tips and some recommendations in case you want to implement something similar at your site. And at the end, we'll have some time for questions. So about the project. In the beginning, we had a site. This was a single site where we were providing some services that they are represented by S1, 2, and 3. This single site was fully redundant. So we had a redundant internet access, we had redundant firewalls, we had redundant load balancers. The servers were redundant. We had server farms, some systems were clustered, we had replicated databases. So everything was fully redundant, although we were not protected against catastrophes. So that's why we had to build the BCP, that stands for Business Continuity Plan. Basically, it's a plan that says how do you survive a catastrophe, say a fire or a flood or a major power outage in the data center or a fiber cut, so whatever you can imagine that would take down the data center completely. On the other hand, we are committed to SLAs, the service level agreement. I will speak about that in a few minutes in more detail. We also had the product people. Those are the ones that are responsible for the product that are provided on this site, so the services. And what the product people want is they want something that is easy to scale. They want something that can grow and shrink according to the business. If you have one customer today, they might want something that scales to 1,000 customers, 1 million customers tomorrow. And on the other hand, you have the technical operations people. They say, well, we want that, but we also want something that is easy to manage. So the question is, how do you build something that can survive a failure and still fulfill all these wishes? So regarding the SLA, that I wanted to speak a bit in more detail, the SLA at Swisscom, it's an agreement that we have with our customers. And this agreement, it's done in the contract. So the SLA is about the service availability. We guarantee to our customers that a certain service is available a certain amount of time. But what is available? How do you measure that? So available is being able to provide that service within a predefined amount of time. But provide means that the service can or has to answer, but it also has to answer correctly. So to give an example that I think everybody understands here, take DNS. When you need to translate a name into an IP address, your resolver asks the first name server to make that translation. If the name server does not answer within a few milliseconds, you fail over to the next name server. And so on and so forth, until you run out of name servers, and you have to assume that your service is failed. But if your name server answers, but it does not answer correctly, well, most likely your service will also be broken. So it's not only answer to a certain service, it's also answering correctly. And when you know when you know this timeout, in which amount of time do you have to answer and what you have to answer, then you can measure it. To give you an idea of some of the numbers that we have at the Swisscom contracts, take the 4 nines are, or they tell the customer that the service will be maximum down a little bit more than 50 minutes a year. But if you take the 5 nines, this is also a typical number that you see in some SLA contracts, that doesn't give you more than 5 minutes downtime a year. Well, that's really, really short. Even if you have a backup, say on tape or even on disk for fast restore, well, it's virtually impossible to restore a system in 5 minutes. So we had to build something, and what we built was a backup site. And on that backup site, although a little bit smaller, because we did not have to provide all the services with this level of SLA on the backup site, so although a little bit smaller, we had to provide also the same services that were also available on the primary site. We built a link, a back-end link between both sites for data replication. This is important. In case you want to replicate the data to a backup site, you need a connection so that if you have a cluster for a cluster heartbeat or a database that you need to replicate. The idea is that the primary site would attract all the traffic. So all the traffic would be routed to the primary site, and in case of a failure, the traffic would be rerouted to the backup site. So by meaning rerouting, I mean this failover has to happen on the network. So with routing. Our goals in this project were to make this failover selective. See, S1 goes down. In case a service goes down and only that service goes down, selective means only that service gets rerouted. On the other hand, we have to be sure that the service is really down. And once we are sure the service is down, we have to fail over very fast. By fast, I mean a couple of seconds. We also have to do it automatically, so no manual action must be involved. And, well, last but not least, we have to do it cost efficiently. This project was not initially planned. We built a backup site for the business continuity plan, for the major catastrophe. So we just decided to make this failover as a side project, since the backup site was already there. We did not have a large budget for this, so cost was very important for us. But important is to retain the failover happens on the network. So just to recap the goals, I said selective, reliable, fast, automatic, and low cost. So what we have used to implement this? We have used Nitrous. I think most of you already know Nitrous. I will speak about it, or I'll show a screenshot later. Nitrous is a network monitoring system, but as opposite to most NMSs, it can use SNMP or ICMP to check if a system is reachable, but Nitrous works with external plugins, and these external plugins are checks you do at the application level usually. So if you have a web server, so you check the availability of your web server, HTTP for example, or if you have a mail server, so it just does the check on an end-to-end from the client to the server, and it checks the response, and it can verify if the response is correct, and if not, it can execute external commands to, say, self-heal the system. We have also used the Quagga BGP router. I couldn't find Quagga logo. I don't know. I guess they don't have one. So I took the logo from the previous project where Quagga is based. It's the Zebra software router, but actually we have used the Quagga BGP router. You can imagine to interact with the network using BGP, of course. And then we have used some expect scripts, self-made expect scripts, just to interact with the Quagga through Nitrous. So at least one of our goals is already reached, which is the low cost. All of these tools are available at no cost, so there's only the cost of implementing this project. So how did it work? We have placed 2 servers on the primary site. Actually, they are on the primary site, but they are outside the cloud. They are in front of the primary site's perimeter, so before the site's firewall. On these two servers, we have installed Nagios, and we have also installed Quagga BGP routers. And we have built some peering sessions with our ISP. Actually, in Swisscom, the ISP is also Swisscom. But it's another group, and we have built these peerings, and we have advertised the prefixes of the services that we want to failover individually. This is important, so we advertise single prefixes, so the /32, it's a single IP address to the backbone of our provider. And our provider, or the ISP, does the same on the backup side. He also advertises the same prefixes on the backup side, although there he advertises it with a higher metric. And as you might know, in routing, metric is like a distance. So the higher the metric, the higher the distance. If the provider advertises the same prefixes on the backup side, but with a higher metric, that means with a higher distance, this route will never be preferred. Although, if you stop advertising that route on the primary side, the network will converge and adapt to the backup side. So because Nagios does the checks selectively to each service individually, it can interact with Quagga BGP router selectively for each prefix. So another of our goals was also reached, which is selectively. Give you another example how this works in practice. Most Nagios default installations, they define that after 3 consecutive checks detected as being down, the service is down. Although Nagios has a very convenient feature, which is if you check, for example, every 5 minutes, you do a check, you do a poll of your service every 5 minutes. But once you poll and you detect the service is down, Nagios has this convenient feature, which is it reduces the polling interval to, say, 2 minutes. So if you define 3 consecutive checks as the service being down, you poll every 5 minutes, but then you reduce to 2 minutes once you detect it's down, say, gives 5 plus 2 plus 2. That means 3 consecutive checks. It gives a maximum of 9 minutes. If your service fails, in 9 minutes, Nagios will detect that. It will run an expect script that will interact with the Quagga BGP router, and this one will then remove the advertisement on the network. And conveniently, the backbone will converge and reroute only that service to the backup site. Now, because you have 2 views of the backup site, because the backup site has a higher metric, as I said before. Now, because you have 2 views of the service on that primary site, 2 views means 2 Nagios are polling the service. They both have to see the same thing. You say that, well, if they both see the service down, then definitely the service is down. So, and once they stop the advertisement, that also the convergence of the backbone happens very fast. BGP converges is a protocol, a routing protocol that converges very, very fast. So it goes about 12 seconds until you have the failover to the backup site. Now, when does this failover happen? Well, it happens when the service goes down. It happens when the entrance of your site's perimeter is down, for example, the firewall. It happens when your pollers goes down. It also happens when the primary site completely goes down. That's what actually we initially wanted to survive a major catastrophe. And actually it also happens if your internet service provider routers go down. So if everything on the primary site breaks, that means that the failover will happen. That will happen for all the services, of course, but it will happen. And it will happen automatically. So you don't have to do anything. You just have then to eventually rebuild the primary site again. So I give you here a screenshot for those of you who never saw the Nitrous Console. On the left side you have a service menu, then you have one column with the hosts, then the checks. In this case everything is up, which is good. But this is basically the Nitrous Console, gives you a view of your service availability. Here's a screenshot of our our two BGP routers, the Quagga BGP routers. It looks very much like the Cisco iOS. For those of you who know Cisco, it looks very much like Cisco. You can give the same command, same style, and you can just build the BGP peerings with your ISP, just like Cisco. You have a terminal, and it's very easy to interact with it through expect. Let me give you some tips and also some of the constraints we have found in this project. So, one IP per service. This is, for example, this is important. If you want to failover, you have to failover a service. You have to reserve one IP for each service you need to failover. For example, if you have a web server and a mail server running on the same host, if one fails, that IP will be stopped advertised on the backbone. So the both services will fail over. If that's not what you want, you have to give one IP for the mail server, one IP for the web server. The same, for example, if you have a Apache with many virtual hosts. If you check them, they are all on the same IP. If you check them individually, if one fails, all of them will fail over to the backup side. So if you want to implement something like that, be aware of this constraint. You have to reserve one IP per service. Another important thing is to protect the pollers. As you have seen, these Nagios, Zebra, or Quagga BGP routers are exposed on the internet. So you have to protect them. As you all know, if you put a server directly on the internet, very soon you will start having strange traffic to it. So you have to put some kind of protection on these systems. So the recommendation is run an external firewall or run a firewall on the external interface. This will prevent that traffic to this box will hit or it will harm the machine. These systems, they don't have to communicate with the external world. They just need to send traffic outside to poll the site internally, and they just need a BGP peering with the ISP's routers. Another idea is do not set up a default gateway on these boxes. They don't need access to the internet. So don't define any default gateway, and you almost don't need a firewall in this case, although it's still better to have one. Also, be aware of BGP dampening. I'm not sure if everybody knows what this is. BGP dampening can happen if you advertise and stop advertising a prefix many times within a short period. So your provider most likely will be protected against this situation, because he will think that your router is unstable, you are flapping, and he will say, I will not accept any advertisements from you anymore during a certain amount of time. So your failover is compromised in this situation. So what you can do to avoid, well, you have to talk with your provider. Probably you have to ask him to whitelist your routers from this route map, probably for BGP dampening, or you have to be careful. Don't advertise and stop advertising the prefixes that often, otherwise you might be blacklisted by your ISPs. Also, forward the checks to a master Nagios. This is a good idea because, as you've seen, you have two Nagios, you have two consoles, you have two views of the system. Usually they both see the same thing, but it might be that they see, one sees the service down, the other one sees the service up. It's not convenient to have two views of the same service. So the best is, Nagios supports this functionality, so forward the checks to a master Nagios and then centralize all the checks in one console, and then you have one single view of your services. And this is a very important one. Also, poll the backup site. Well, the backup site is there to save you at the end of the day. So you also have to be sure that the backup site is running. So how you can do that? I have a slide to explain how this can be done. As I said before, we have placed a Nagios and a Quagga BGP router on the external network of the primary site. You can do the same on the external network of your backup site. You just need a Nagios there. This system should poll the services on the backup site and verify if these services are available. If not, forward an alarm to your operator so that they can fix the problem. It's important to note here that what I call here as 1P for primary and 1B for backup, these two networks, they don't have to have the same IP addresses. So you only have to have the same IPs inside the site, in the clouds. Outside, you don't have to have the same IPs. So if you want, these systems can also be reachable from the outside. So you can have a view of the services from the outside, from your operator stations, in case you don't have back-end connection, so that you can connect to the boxes. Now, some improvements you can do. We actually didn't do all of these. So you can reduce the timers. I gave the example of the 5 + 2 + 2 minutes. That gives 9 minutes to detect that the service is down. But you can reduce that. You can reduce that to poll every minute, reduce that to 30 seconds if the service is detected to be down. So you will detect that the service is down very quickly, and that will allow you to also fail over much faster. You can also do an automatic site failback. That means if the primary site, the problem on the primary site is fixed, the pollers could detect that and could re-inject the prefix on the primary side. That means that the backbone would again converge back to the primary site. We haven't done this because we don't want the sites to fail back without manual human to verify what went wrong there. But it could be done. Nitrous also allows you to do that. Also detect quagga splits. What I call here quagga splits are, for example, when one quagga BGP router advertises a prefix and the other one doesn't. So they have, the service will not fail over because at least one is still advertising that prefix on the backbone, on the primary side, but something is wrong. At least one of them is not advertising it, so you should detect that. You should know why, and so this is something that could be done. Also with a check on the quagga itself. And finally, you could have more backup sites. So if you want diversity, you could fail over to a backup site, and if something goes wrong on that backup site, you could fail over to another backup site. So you could use some kind of GeoDNS to attack the traffic to the most closest site of your users, and then fail over to the second closest one, for example. And with this, I terminate this presentation, but not without saying that coming here today and sharing this information with you is, first of all, thank you to the open source community for their work, not only regarding these tools, not only regarding the tools we have used here, but also regarding all the great open source software that we also use at Swisscom in other projects. So thank you for your attention.
Okay, thank you for the speech. If you have questions, you can ask now. Please speak into the microphone, it will be recorded.
Thank you for your presentation. It's very clear. I want to ask to you how you can, you speak about routing problem,
right?
But another big problem is to keep synchronized information, like information stored in database or in file system. What kind of tool do you use for this problem?
I'm sorry, I'm not sure if I understand the question. The question is, how do we...
For this, or better, which kind of service do you use this type of switch off?
What kind of
service?
Service do we?
I mean DNS, web server, or like that. And how you can keep synchronized information? Okay,
so the question is, how do we synchronize the data related to the services we provide on this site? Okay, the presentation is pretty generic. I didn't want to go in detail regarding the services that we provide on this site. I can tell you it's a lot of services. For company reasons, I don't want to go in detail there, but well, the way you can replicate the data between both sites is the best way is to have a backend connection. You can also do this replication over the public internet, although this is not recommended, and if something fails in your perimeters, the replication will also be compromised. So the best way, and the way we have done it, is we build a backend connection that interconnects both sides, and with this we replicate the data. If we have a web server, we synchronize the data on the file system. If the web server uses a database, we replicate the database. If we have a DNS, for example, well, it's easy. You can have a DNS slave on the backup side, for example, ready to answer the queries. So I'm not sure if this answers your question. Okay. So you want to know if we only use open source software for these services?
Do you use open source for replication?
Yes and no. For the services, it depends what the service is.
Do you use a distributed file system, for example?
I'm sorry?
Distributed file system, DFS, like OpenFS
not on this site. I can say all over Swisscom, but not on this site.
Thank you.
Okay, if are not more questions, I quit now. Here. Thank you very much.
Thank you.